So today we're going to be going through the column from 76 to 84. So without further ado, let's go ahead and jump into question 76. Okay, so we want to find the limit as x approaches 6 of this graph, or this equation right here. So x squared minus 36 or x minus 6. So let's take a look at that. Let's give ourselves a little more room to work with here. Okay, so our first response is always with a limit, can we just immediately plug it in? So let's try plugging it in. Okay, so if I plug in a 6, I will get 6 squared minus 36 over 6 minus 6, which gives us 36 minus 36 over 0. Boom, we have ourselves a problem. This is indeterminate. Can't figure that out. So plugging it in didn't work, but one of the other methods that we could do, and let's do this in, let's say this is in purple, is can we manipulate the graph? Or manipulate the equation. So I'm going to see if I can't manipulate this equation to maybe cancel some things out on the bottom, which I notice I have a square to the top, which means maybe I can factor this. And so that's exactly what we'll do. We're going to factor the top, which is a difference of squares, into an x plus 6, x minus 6, all over x minus 6. Lo and behold, we notice that when we factor it, these cancel out. I'm left with an x plus 6. And now I'm going to try and plug in my 6. Not as x minus 6, as x approaches 6. Silly goose. So now when I plug in the negative 6, I will get negative 6 plus 6, which is 0. So we know the limit algebraically is going to be 0. Boom. So we don't need to do the graph, and we don't need to do the table method because we got a method via the algebraic process. If we wanted to do the graph, all we would need to do is take a peek at this. So let's go ahead and plug this in. We have a numerator of x squared minus 36, closed numerator, divided by denominator of x minus 6, closed denominator. Okay, so what we notice is this looks like a straight line. And so as x approaches 6, let's go ahead and trace. As x approaches 6, we're kind of off our window. So let's give our y, how about some height here? There we go. So let's trace it. As x approaches 6, we notice it moves smoothly over that value between 11 and 12. Oh, I plugged in a negative 6, that's why. Okay, plugged in a negative 6, again, because I misread my own writing there. But it's a good thing we checked that. So between 11 and 12, I got my value. However, if I tried to plug it into a table, let's do our table by asking us. So if I try to plug in a 6 as of right now, it's an error. But if I plug in a 5.999 and a 6.001, I'll get numbers right around 12. So I know that there must be a hole in the actual graph. So the graph is continuous on both sides of it, but we plucked out a little point. Actually, by definition, it's not continuous. Okay, so that was number 76. Let's take a look at number 77. Okay, we want to find the limit of e as x approaches pi. Okay, so with this one, we would attempt to plug it in, but there's nowhere to plug in the x because there's no x in this equation. This is a horizontal line at e. So if I were to sketch a graph of this, here's my x, here's my y. This graph is a horizontal line at y equals 2.71828, ... all the values of e. So as x is approaching pi, this arbitrary point along the graph, so we have 1, 2, 1, 2, 3, and pi. Our graph is still at that value. So I know that this is going to be e. We don't need to do any sort of fancy math here. Okay, so that was number 77. Let's take a look at number 78. Okay, so we want to find the limit as x approaches infinity. As x approaches infinity of this expression right here. So we have 2x cubed plus 3x minus 18 all over 8x minus 4x fourth plus x squared. I'm going to put this in parentheses because we have a numerator and a denominator here. We don't want to get these confused. Okay, so let's give ourselves some room. So our first try is always to try and plug it in and see if it works out. We're about to find out that's not going to work, but let's go ahead and do it anyway. Plug it in. When I try and plug it in infinity, I get 2 times infinity cubed plus 3 times infinity minus 18 all over 8 times infinity minus 4 times infinity to the 4th power plus infinity squared. If I simplify and get rid of all the powers and coefficients, what we'll notice is that we get 2 times infinity cubed is infinity, 3 times infinity is infinity, minus 18. So the numerator reduces down to infinity. The bottom I have infinity minus infinity plus infinity. So with this, I have infinity minus infinity. Don't really know what I'm going to do with this. I don't know which infinity is bigger, top, bottom, left, right. So this is what we're going to call our indeterminate form. I can't do anything with that. So plugging it in didn't work. Surprise, surprise. We had too many variables going on. So what we're going to do is we're going to try manipulating the equation. Okay. And one of the things when we see a rational function where I have x's on the top and the bottom, if I can't factor them out, I'm going to, or if I can't factor the overall polynomial, I'm going to factor out the largest power of x that I can. So on the top, I have an x cubed. And I'm going to highlight this so we can spot that. X cubed. On the bottom, I have an x to the 4th. And we'll see why we pull that out here in just a moment. So I'm going to factor out an x cubed, even if I can't. So in the first one, I can. The second one I can't. I only have a single x, so I'm going to say, well, that's 3 over, I need 2 more x's, so I'm going to put that over x squared. Minus, I have nothing to pull out of the 18, so I'm going to say 18 over x cubed. I'm still going to pull it out, even though I technically don't have enough room for it. On the bottom, I'm going to pull an x to the 4th out of all 3 of these. I'm going to have the 8. I need 3 more x's right here. The 4 is okay. This is going to be a 1 over x squared because I pulled out 2 of them, but I still needed 2 more. What this allows me to do is it allows me to cancel out some of these things over here on the left. I have 3 x's up top and 4 on bottom. Let's do this in, how about in blue, which leaves me with a single x on bottom. That single x on bottom, I'm going to then feed right back into this. So I have 2 plus 3 over x squared minus 18 over x cubed. Once I feed this in, I will get an 8 over x squared minus 4x plus 1 over x. Okay. Now when I've gotten to this point and I've factored out the largest possible values, I'm going to revert back to plugging it in. So now when I plug it in, I have 2 plus 3 over infinity squared minus 18 over infinity cubed. On the bottom, we have 8 over infinity squared minus 4 times infinity plus 1 over infinity. Now what we notice is anytime we take a finite number and we divide by infinity, I'm taking that number and I'm splitting it up so small that it doesn't exist. So each one of these terms that I'm dividing by an infinity cancels out to 0. And so the only term I'm left with on the top is a 2, and the only thing I have on bottom is a negative 4 times infinity, which is a negative infinity. 2 divided by negative infinity is a 0. Technically, it would be a negative 0, but we know this is going to be 0. So therefore, we know the limit as x approaches infinity of this equation is going to be 0. Awesome. So we could check that out, make sure we did it right, if we have the use of a calculator on this question. So let's take a look. Let's go ahead and clear our last one. We have numerator 2x cubed plus 3x minus 18, close numerator, 8x minus 4x fourth plus x squared, close denominator. Let's set this window back up from negative 10 to 10. Take a peek at the graph. Okay. So notice the graph is very, very, very tight down here. So I'm going to close the window just a little bit from negative 1 to 1. So we see the graph is curving up. We might see a little peak right here, but I see it dips down and starts curving back up. So that's where that negative 0 comes in, is I'm approaching 0 from the bottom. In fact, if I plug in larger and larger numbers, let's delete these, I'm close to 0, closer to 0, really close to 0. Let's see if we can get the calculator to round. Nope. Nope, the calculator is determined not to round. But it's getting closer and closer and closer to 0 from the bottom there. So we're very safe to say that our limit is actually going to be 0. So that was number 78. Let's go ahead and swap over to a new sheet of paper for 79. Okay. So 79, we're going to find the limit as x approaches 0. Of x cubed plus 7x squared plus 10x, all divided by x cubed minus x squared minus 6x. Okay? So with this expression, we're going to try and do the same thing that we just did. Our first expression, or our first try, is always going to say, hey, can we plug it in? Because that is always going to be the easiest way to figure this out. So I'm going to try plugging in 0. So I get 0 cubed plus 7 times 0 squared plus 10 times 0. On the bottom, I get 0 cubed minus 0 squared minus 6 times 0. This evaluates out to a bunch of zeros over a bunch of zeros. Indeterminate, can't do anything with it. So I'm going to have to manipulate this equation just a little bit. So if I manipulate the equation, I notice that they both have an x. I can do the same thing that I did with infinity, but I'm plugging in a 0, so I don't want to end up with a bunch of fractions where I have to plug in a 0 on the bottom. 1 is enough right here. I don't want to have possibly 1, 2, 3, 4, 5, 6 of those. So, but what I do notice is that every single one of these terms has an x. So why don't I factor out an x? So x squared plus 7x plus 10, x squared minus x minus 6. Okay. Those x's now cancel out. And I'm left with x squared plus 7x plus 10 over x squared minus x minus 6. Ooh, this looks a lot better. So let's revert back to the plug it in technique. Okay. I'm going to plug in my zeros now. So I have 0 squared plus 7 times 0 plus 10 over 0 squared minus 0 minus 6. So I notice I have a bunch canceling out, but my last terms don't. So I'm left with a 10 over negative 6, which is a negative 5/3. So I know the limit as x approaches 0 of this expression is going to be a negative 5/3. Boom. And so let's go ahead and actually graphically check that. Make sure, like on our previous one, that we didn't make some sort of common mistake where it plugged in the wrong number. Okay. So let's go ahead and try this out. Numerator x cubed plus 7x squared plus 10x, close numerator, cubed minus x squared minus 6x, close that, and as x approaches 0. So first off, I'm going to check out the graph. Oh, we're still very much zoomed in. So if I go from negative 10 to 10, that should clear up my graph. Okay, so it looks like we've got, as x approaches 0, it's approaching a value. So far so good. Let's check our table. Let's plug in numbers really close to 0. 0.1, 0.001, 0.0001. negative 1.67, which is negative 5/3. And if I go from the other direction, negative 0.1, negative 0.01, negative 0.001. Again, I'm approaching that same value from both the left and the right. So therefore, we're very confident that is the correct number. Okay. So that was number 79. Let's go ahead and take a look at number 80. Which function is not continuous at x equals 2? Okay. Well, we know that at x equals 2, let's try and plug this in. Okay, so A, we have f of x is equal to x squared minus 4x plus 4. This function doesn't have any sort of break. This is just a quadratic that opens upward. There's no reason for this function not to be continuous at a number. So this function is just going to be continuous, because there's no reason for this to have any sort of break. If we look at B, x squared minus 4x plus 4 all over x plus 2. And we're checking at x equals positive 2. There's a chance, because I have my denominator, I'm dividing by something, so there's a chance that I can't plug in a value. So I'm going to try this out and say x plus 2 cannot be 0. X cannot be negative 2. That's okay. The positive 2 is what we're checking for. As long as it's continuous at positive 2, we're happy. So this is continuous at x equals 2. Okay. Option C, we have g of x is equal to, curious as to why we have f and then g and then g and then g again. But x squared minus 4 over x plus 2. So again, we run into the same thing. I have a division sign right here, so I'm going to check and make sure that that x plus 2 can't be 0. Well, again, it's at negative 2, so I know this graph is also continuous at x equals positive 2 is what we're checking for. Okay. Option D, we have g of x is equal to x squared minus 4 all over x minus 2. We have a denominator that we have to check. Does x minus 2 cannot be 0? X cannot be 2, which means that this is discontinuous. So, not continuous at x equals 2. It is removed. It's not an asymptote, because if I were to factor the top, I know the x minus 2 would cancel out. And that is a very common mistake that a lot of people make, is they'll say, well, hey, this is an x plus 2, x minus 2 over x minus 2. They'll cancel those two terms out and say, well, this is really just an x plus 2. But remember, this point was removed. So albeit the graph looks like it's continuous, if I were to check out the shape of it, there's a hole in the graph at that value. Infinitely small, but there is a hole. So this one is the one that is not continuous at x equals 2. Option D. Okay. So that is going to be the end of that sheet of paper. And let's get a new one. So let's get a new sheet of paper for 81. Oop. Close enough. Okay, so for 81, let's take a look at what we're doing. Given that g is a continuous function on the interval 1 to 5, and g of 1 is -1, and g of 5 is 7, what does the intermediate value theorem guarantee for the function g? Okay, so it's a continuous function from 1 to 5. So on our x-axis from 1 to 5, this function doesn't lift up. At g of 1, we are at -1. So doesn't matter exactly. We're not necessarily doing this to scale. So at g of 1, we're at -1. And then at g of 5, we are at +7. What does this guarantee for the function g? Well, in order for this function to get from here to here, it must pass through a 0. Now, we don't know where exactly that 0 is, but we know it must be there because the function has to be continuous. No matter what we do, if I wiggle the function down here and then shoot up at the very end, it still has to hit a 0. If I have the function shoot up immediately and then wiggle up here, it still has to hit a 0. The only way for this graph to skip the axis is to either go for a bit and jump across it. That would be a point where there would not be a 0, but then the function is no longer continuous. Or if there's something like an asymptote. Running out of colors here. So let's do orange for this last one. So let's say I want to avoid it. Well, I'm just going to go straight down. And then as I go straight down, I'm going to have an asymptote come through here. And then we'll come down from above until I, nice and easily make it to my point. But that, again, is a point of discontinuity, either a jump or a break, or really, if you wanted to, I'm completely out of colors here, is we could have a hole in the graph. Let's say the hole was at the 0, but again, that is a point of discontinuity. The only way we're avoiding this axis is if we break continuity. So if the function is continuous, the intermediate value theorem guarantees there will be a 0 somewhere between -1 and 7. So the function g must have, let's set this up right here, must have at least 1 0 between g of 1 and g of 5. The reason why we say at least is the function isn't limited to just passing once. If I want to wiggle right along this line and have a lot of zeros, I can. But it has to have at least 1 because the minimum amount that I could have is 1. Awesome. So that was number 81. Let's take a look at number 82. Okay. Using the intermediate value theorem, given that f of x equals 2x squared minus x minus 5 is a continuous function, we know that it is, it's a quadratic, does f of x have a 0 over the interval -3, 1. Why or why not? Okay, so this is an extension of our previous question, so let's copy down this. So f of x is 2x squared minus x minus 5, and we're checking over the interval from -3 to 1. Okay, well, from -3 to 1, we want to check out exactly what we just demonstrated right there. What is the graph doing? So our first step is to evaluate it at -3. So let's figure out what that is. So f of -3 is 2 times -3 squared minus -3 minus 5. This gives us 2 times 9 plus 3 minus 5, which is 18 minus 2, which is 16. Okay, so our first value is at 16. Let's take a look at the endpoint. Okay, so at 1, copy this down with 1. F of 1 is 2 times 1 squared minus 1 minus 5. So 2 times 1 minus 5, 2 minus 6 is -4. Oh, f of positive 1 is -4. Okay, so given that information, the graph from -3 to 1 goes from a positive value to a negative value. And we know that it's continuous, meaning we can't skip a point. We can't have a removable discontinuity, a jump in the graph, or an asymptote. So without sketching the entire graph, we're just going to go from -3 to 1. We know the point f at -3 is at 16, and the point at 1 ends up at -4, again, not drawn to scale. And the only way that this graph is going to get from here to here is by somehow, oh, I'm trying to avoid it, oh, I gotta go through the axis. We know that's not the shape, but I know that I've got to go through it no matter how I try and bend and avoid. That is impossible to not cross over. So let's reread the question, make sure we're answering this correctly. Okay. Does the function have a 0? Why or why not? So let's go ahead and say yes. The function f of x must have a 0. We're going to leave out the at least because we know with a quadratic, it's either going to have 1 or 2. Must have a 0 between -3 and 1 because it changes from positive to negative. And the only way that we go from a positive number to a negative number without picking up our pen is to cross through that one number that is neither positive nor negative, which is 0. Perfect. Okay. So that's 82. Let's take a look at 83. Okay. We are going to use the definition of continuity to determine if f of x is continuous at x equals 2. Explain. Okay. So at x equals 2, it's right here. We can already tell visually that that is not continuous. If I were to trace this graph along here, I would have to pick up my pen, place it down for here for just a moment, pick it up again, place it right here, and then continue on. So the definition of continuity is a series of unbroken connected points over an interval. So definition of f of x being continuous at x equals 2, meaning it's a series of unbroken points where I do not need to pick up my pen at all. Series of unbroken points, breaks, and breaks again. So f of x is not continuous at x equals 2 because the points on the left, on the left of 2 and the right of 2 are not connected to each other, nor to the point at 2. So the definition means they must all be connected. The points to the left and to the right aren't connected to each other because there's that small, small, small gap, and they're not connected to this point. So I think that's a very safe, very good definition of what's going on here. Okay, so that's number 83. Let's take a look at number 84. Okay, so 84 is a three-parter, so what we're going to do is we are going to pop down a new sheet of paper just to make sure we get all three on the same one. Okay, so what we have right here for 84 is we have the limit as x approaches some value a of f of x is equal to 4. We also have the limit as x approaches that same value of a of this other equation, g of x, sliding things all around here, is equal to 7. And what we want to find is the limit as it approaches that value of f over g. Okay? The limit as x approaches f over g, I have the limit as they both approach it. So the limit of this is 4, the limit of this is 7. So for a, I know it's going to be the limit of f of x divided by the limit of g of x. It's going to be 4 over 7. Okay? Well, let's go ahead and draw a line. For b, 84b, we want to find the limit as x approaches a of f of x times g of x. Well, I know f, I know g. It's going to be 4 times 7, which is 28. Limit as x approaches the number of 5 times f of x. Well, 5 times f of x is going to move its limit up 5 times, so 84c is going to be 5 times the limit of f, which is 5 times 4, which is 20. And there we go.